All right. So a couple of notes. So quiz, all right, that I passed back. Solutions are all posted, and I curved the tests if it so deems. Be aware that again, like your home funds and your activities, if I put those scores in, they are uncurved quiz scores. So I highly encourage, again, home fund and activities, definitely where you want to spend your time. Like after I look at all the scores, I decide if I'm going to put a curve on it. That chapter 5 part 1 is stuff we're going to be doing the rest of the semester. So definitely any problems you missed, go through, look at the solutions, redo those problems, resolve them, make sure that all that stuff comes into play. And one thing I made a slight mistake on my part. How many feet are in a mile? 5,280, right? We talked about it in class. It technically wasn't on the quiz. All right. So slight mistake on my part. But again, I feel like some of those things we should know. I'll try and be more cognizant of that, like that maybe not everyone has those conversions memorized. Like I was like, I apologize for that. That was pretty much the only thing that I saw that you shouldn't have known, that you might not have known. All right, everything else. And I think one thing that definitely needs some emphasis was basically on that number 2. I think you guys underestimated the usefulness of CAT, complementary angle theorem. When two angles sum to 90 degrees, the point is to get them to the same angle. Everyone was doing all kinds of mess, and I saw very few people using CAT. All right, so go through and resolve that problem and think CAT first. All right, complementary angle theorem is the biggest theorem. All right, when it looks like it's a mess, you use complementary angle theorem, and then all of a sudden it's something beautiful. All right, and that's going to keep coming back around. All right, take a look at your quiz, look at the solutions, and then we'll have some time next time, and you can feel free to ask me questions. As for today, we have already started the lecture for chapter 5, part 2, and we're basically going through the 6 basic trig function graphs. We had already looked at sine, cosine, and tangent. All right, so now we're to all the reciprocal functions. Now, the good news is that a lot of these overlap, just like everything. So much of all the trig identities and trig functions, they're all just so connected. Similarly, the basic graph of cotangent relates very, very similarly to tangent. So the initial first period and cotangent, just like tangent, has asymptotes every pi. And it almost looks exactly the same as tangent. The only difference is that it's actually flipped. It's basically the negative of tangent and then slightly shifted over. But it also keeps continuing just like tangent does. It has asymptotes every pi on the pi, right, on multiples of pi. And it crosses at every pi over 2 multiple. And I mean, cotangent looks just like the tangent function. Range being negative infinity to infinity. Domain is all reals except for multiples of pi, which have asymptotes. All right, what is a slightly different function is cosecant and secant. Cosecant since it is the reciprocal of sine and secant is the reciprocal of cosine, the only way to actually draw these and know what you're doing is to initially graph their reciprocal functions. So let's go back and let's draw sine. Let's see if we can remember how that one looks. So sine is a nice, beautiful function. And then it goes on and keeps repeating. It has important points at 2 pi, pi over 2, and 3 pi over 2. It has a maximum of 1 and a minimum of -1. And so that's our basic graph of sine, which we have at least seen a few times now. So the reciprocal, right, cosecant, is the reciprocal of sine. And this function actually comes in the same way that when we graph it. Basically, everywhere sine crosses the x-axis, cosecant would be, right? So at pi, sine of pi is 0. 1 over 0 is undefined, all right? Which means that at every multiple of pi for the cosecant graph, we end up with an asymptote. Now, that takes care of one piece. And the other nice thing is that everything with cosecant, it's basically then a mirror image off of the sine graph. So the cosecant graph actually ends up looking like a bunch of parabolas off of the sine graph. All right, just to emphasize, it keeps going forever, the pink lines. So cosecant, very, very similar. So notice how sine has minimum and maximum of -1 to 1. Cosecant goes from -infinity to -1, then from 1 to infinity. And there's basically, when we start doing all our shifts and everything, there is no fast way to graph cosecant without first graphing sine. We graph sine or cosine, all right? And then we graph their reciprocal functions. It's just like doing the negatives. So there's a lot of pieces when we graph equations. And we basically just have more and more complex equations. But remember, our big thing is graphing one period. We like to graph just one period. And then I put the emphasis that they are periodic. They go forever in both directions. But usually the biggest information, especially when we start getting into context, the biggest information is always within the first period. That's how you create a graph. And then similarly with secant. So the secant graph, recall that it actually, or sorry, the cosine graph, recall that it actually starts at a peak. It has the same important points, pi over 2, pi, 3 pi over 2, and 2 pi. It is, sine and cosine look like the same graph. They are literally, since they are complementary angles, right? It is the same graph, just shifted. So the first period of cosine just looks slightly different. But when you graph them on top of each other, and we saw that in the calculator, they look like the same graph, just shifted over. So along those same lines, in order to graph secant, wherever cosine crosses the axis, that creates an asymptote. Then the secant graph is a mirror image off of the cosine graph. And so along the same lines, the first period of secant looks kind of funky as well. And it follows the same properties. And again, don't forget, we have our calculator, so if you ever forget what any of the basic functions look like, graph them on your calculator. We talked about it before. What's the big problem with the calculator when graphing functions? Window. Oh, that is a good one. But we hit zoom trig. What's the other real problem?
Can't see where where they cross.
Scale. It's always comes to scale, right? You just can't, there's like no good way unless you know, oh, plug in 7 pi over 12, you know, use value 7 pi over 12, and then it turned out to be 1. And you're like, oh, I just guessed it. Good for me. Okay. So that's the problem. It's what the scale is. But you can always graph it and see an approximate picture. So at least like, wait, was I graphing like, for some reason, I forgot what secant looks like. I just don't remember. Is that this one? Like, is that this one? Right? So it can at least remind you, oh, it's the one with a bunch of parabolas, basically. All right. Okay. So, just like with algebra, once we identify the basic graphs, and now we have 6 basic trig graphs, what we start doing is we start messing with them, and we already started messing with sine and cosine a little bit. All right, we're going to continue to do that because we can mess with all of them. All right, any of the 6 trig functions. You have to keep remembering those basic little adjustments. So I have y cotangent of x minus 1. It doesn't look like this is messed with too much, but we just got to remember. So what's that? So it's almost the base function. It's just that -1. What's that -1 do?
Down 1.
Moves it down 1. And that's absolutely correct. And again, this is exactly an algebra concept. So we have our function, all right? And then remember what the basic, all right? The technical first period of cotangent is this guy. But if you ever graph one period, all right, it doesn't really matter. I was like, pick a period. You want to start at 5 pi over 2, you go nuts, okay? As long as you can appropriately graph one period, that's all that matters. It's always just easiest to start with, you know, the one closest to the x-axis or y-axis, the origin. All right, so it's basically that, pi over 2, but now shift it down. So down here I have -1. I still have an asymptote at pi. The graph should then still start at pi over 2. And sometimes, right, we actually say BA 0, BA x equals pi. I was like, with the repeating ones, if you want to just further identify it, graphing these is so nice to graph in color. You can see the colors are too much shade. And then same graph. Oops, wrong way. And again, simply the cotangent graph shifted down. And then they keep repeating forever and ever. So again, not much happening on this one, as long as we can make our basic adjustment. And again, gonna start breaking these down piece by piece. We looked at we looked at like 1 or 2 examples of entire sine things, tons being shifted. All right, gonna slow it down and look at smaller pieces. All right, so secant, which means in order to do secant, I really need y equals cosine of 2x. Because without graphing cosine, I don't know how to graph secant. Okay, so I have cosine, and just one little thing. What is this 2 being multiplied by x do? How does that affect it? Do we remember?
Stretches it, doesn't it?
Stretches it, all right? I was like, but I mean, stretching a graph that's periodic is kind of a weird thing to say.
This way though, isn't it?
Oh, it's not amplitude. Ah, I see what you're saying. So the amplitude is the number that would be in front. Okay, that's the one that stretches it this way. Okay, yes. And stretches is an appropriate way to say that. This affects the period. So remember that t equals 2 pi over omega, where this value that's being multiplied by the x is always omega. So that changes, all right? And remember that for sine, cosine, secant, cosecant, the period is 2 pi. What's the period of tangent and cotangent? Pi, right? Those graphs repeat every pi, all right? Secant, cosecant, all of these, in order to graph one full period, we always graph 2 pi of these. So they're slightly wider graphs. So that means we just have to adjust the period. So this becomes 2 pi divided by 2. And oh look, now the period of sine or of cosecant and secant is now pi. And that shifts. All right. So remember, how many points do we need in order to properly graph sine and cosine? 5. All right. We need 5 points. In order to graph tangent and cotangent, how many points do we need? 3. I mean, 3 is the minimum because that identifies the asymptotes. I mean, it's almost 1, right? But 3 is the right number because I want to identify both edges and then the middle, because the other points aren't as important. But in order to graph and sine, cosine, and the reciprocals, we need 5 points. Now, the good news is that in our basic graph, the 5 points are pretty easy to identify. 0, pi over 2, pi, 3 pi over 2, 2 pi, all right? They are the axes on our unit circle. And again, actually at this point, once it hits 2 pi, it's technically repeating. This is basically a exact repeat of the first point. Okay, so we need 5 points. And if the period is 2 pi, the good news is, in order to find those 5 points, without anything else happening, it's going to be pretty simple. So my first point, it was 0, it's still 0. My end point was 2 pi, and now it's pi. And before, right, we were doing, start plus the period finds the end. Start plus end divided by 2 finds half, but actually we could do it even easier. What's halfway between 0 and pi?
Pi over 2.
Pi over 2. What's a quarter of the way between 0 and pi? Not a trick question.
Pi over 4.
Pi over 4. Do we see the pattern? What's 3/4 of the way between 0 and pi? Someone besides Macy.
Pi over 6.
Nope.
Pi over 8.
No, we get rid of the pi. This is 0 to what?
Pi.
Get rid of the pi. Get rid of degrees, radians, everything. What number is next to pi here?
2.
1.
1. 0 to 1. 1/4, 1/2, 1. Guess what goes here? 3/4, AKA, now put the pi back in. 3 pi over 4, right? Don't overthink it. I know, that's what I was talking about. That pi, everyone's just like, oh wait, pi over 8, pi over 9, pi over 11, all right? It's just a fraction with a pi, right? I was like, think back to the base form. And we're gonna need to do those once with the formula, you know, start plus n divided by 2, and then start plus half divided by 2 in order to find those. But this is one where if you we're fast with fractions and remembering that pi is just a number being multiplied by it, right? It doesn't hurt. And this is also why I was saying, initially, a lot of people like to even write it like this. Is that still correct? Yeah. I was like, we write it as 3 pi over 4 just because it looks prettier, right? Doesn't change what the value is at all. All right, so I forgot what we're doing. Okay, cosine. All right, we've got all the values. Nothing else is happening. And, all right, what we actually needed, so this is y equals cosine of 2x, but what we actually needed was secant asymptotes and then, oh, okay, that's sine, isn't it? I graphed sine. Cosine. There we go. Now asymptotes. And then secant. So, and now, here's the big thing. This, and basically every time, they all the graphs look exactly identical. Basically, I draw the same graph every single time. The only thing that is changing, all right, the shapes are never changing. The things that are changing are the scale, okay? The scale, and you know, which, whatever the scale is on the X, whatever the scale is on the Y, it's slightly shifting up or shifting down, but the graph looks identical every time. I graph one period over and over and over again. It never really changes. It's all about identifying that scale, identifying those 3 to 5 points and making sure that the graph then corresponds. All right. We okay? Okay, so we can then do lots and lots with curve fitting. So we're going through piece by piece, changing little things, but we can also go backwards. So I drew a little graph here, and then given what I drew, technically this would keep going forever, but given how I drew it, I wanted you to identify a particular graph, right? Because I can always interchangeably have sine and cosine. But given that this is what the first period, what graph do I want us to start with?
Cosine.
Cosine, right? And always, right, when you keep going forever, and this is my whole thing too, I almost always pick sine because it just feels easier to identify the starting point of the start and end of sine versus cosine. But I really wanted us to pick, because, and they're always just going to be 90 degrees off, right? They're going to be just pi over 2 shifted, exact same graph every time. But for this one, start with our base function, all right? We see this is y equals cosine. Then we need to identify some other things. Okay, so the easiest thing, right, which is what you talked about, Berna. What's the easiest thing to really look at? The stretch, right? What do we call that? Amplitude. Excellent, Jada. All right, we call it the amplitude. Okay, so it looks like this goes from 0 to 4. So what is the amplitude? The amplitude is then 2. Remember, it's the max minus min. So the amplitude is the max minus min divided by 2. In this case, 4 minus 0 divided by 2, that gives us 2. All right. What else do we need? Or what else can we see? You see something, Jada?
Period.
The period. We need the period. Absolutely correct. How do you identify the period? Yeah.
2 pi over omega.
Yes, that's that. If we had omega, this one we're trying to create that equation. I don't have omega. I don't have a starting point of 2 pi. I mean, I can work that backwards. But I was like, the big thing is I don't have omega. So given what I'm looking at here, how do I find the period? Anyone else? Those are my 5 points, right? Not perfectly drawn to scale because I sketched this, obviously. All right. Those are my 5 points. Does that help? How do I find the period? Jada, you keep my one.
No, is it 3 pi over 4?
Is it what?
4?
Is it 3 pi over 4? Is that what you said? That's close. It has to do with this negative 3 pi over 4. And what other big number?
Pi over 2.
Oh, keep going. I mean, I actually could use that if I wanted. But the easier one is, here's the start.
0.
Here's the end. By definition, the period is start to end, one period, and essentially you could say peak to peak, all right? So if we go peak to peak, all right, I can identify the period. It's basically end point the end point minus the start. In this case, my end point is negative pi over 4 minus the start point, which was negative 3 pi over 4. So that gives me positive 3 pi over 4 minus pi over 4, which is 2 pi over 4, aka pi over 2. And again, this is just fraction math, right? That pi, I know it messes everyone up. And so you can pull the pi down, ignore the pi, however you want to do it. So, I actually have the period. Now, I could actually work backwards. Knowing my equation, t equals 2 pi over omega, but now I have 2 pi over omega equals pi over 2, since we identified that as our period. And then it's just a matter of solving. Let's see. So cross multiply, we end up with pi omega equals 4 pi. Divide by pi, omega equals 4. Oh, beautiful. And again, we're trying to create our equation. So, all right, I found omega, right? And in order to get omega, we had to have the period. I found the amplitude, all right? I know the basic function. Okay. Phi over omega, which we call the starting point. That one we already identified as well. What's the starting point?
Negative 3 pi over 4.
Negative 3 pi over 4, right? That's what we're determining. Again, if the graph goes forever, all right, you can pick starting point wherever. Now, if you're picking cosine, I recommend you pick a peak. If you're picking a sine, all right, you want to pick a middle, right? Because remember, sine, all right, actually has pieces above and below. Cosine, all right, starts and ends on a peak. Okay, so the starting point is negative 3 pi over 4. And we need, I think, just one more piece. That should be everything. Is anything else happening to this graph? And what's always helpful is let's look back at our basic cosine graph, wherever that was. All right, so our basic cosine graph, that's what it looks like. So what we're looking at now is anything else different. We identified something different with the period, the amplitude, all right, the start point. What other big thing is different?
Shift it up.
It's shifted up. It is not crossing through the x-axis, okay? Since it is not crossing through the x-axis, we have a shift. So, and that's actually, all right, you guys did leave the easiest one for last, all right? The good news is, so you identify basically the middle line, right? Where is the middle line? And so, yeah, the shift is up 2. All right, don't be tempted. I know a lot of people are like, whoa, I was like, they miscount. Remember, always think back to the basic graph, and the initial cosine graph crosses the x-axis. So sometimes when you're trying to adjust these, draw where the middle line would be. All right, the shift is the easiest one, but it's also the one that people mess up the most because they're like, oh, I know exactly how it's shifted. And then they like right or wrong. So yeah, it's simply just shifted up 2, y shift. And oh, starting point, we also remember we call this x shift. All right, and lastly, y shift, which we identify as the term b, is plus 2. Okay, I think we have everything. So let's see if we can put that all together. Y equals cosine. All right, out front, I have my amplitude, which is 2. My omega is 4. And remember, the form is kind of funky. we have a quantity x minus the x shift plus 2. So putting that all together, all right, because this omega is being multiplied by the entirety of the x quantity shift. And remember, it's always of the form negative because it's always the opposite sign. Now, I could have just written a positive there because it's always just opposite sign, but the general form is negative. You can always just flip the sign. I just wanted to emphasize that it's always subtracted whatever the value is, and it just happens to be negative. So actually, not too bad, huh? Now, feel free to multiply it out. This is absolutely a proper form to leave it because it has all the pieces to go the opposite way. If I start here, I can identify everything. Are we okay? And don't forget, here's the other thing. All right, with these graphs, your calculator is there. If you know all the pieces, now I could actually use value 0 because I know, oh, it's negative pi over 4. So I can actually put into my calculator negative pi over 4 and it would come out as 4. That's the way you use your calculator. You have to know all the information in order to properly use it. That is the slight downside. All right. Similarly, y equals 4 tan 2x. So again, we have lots going on and then bring it back down, just a little bit going on, all right? We have all levels of how much the graphs are being adjusted. So once again, what do I have going on here? What are my pieces? What am I told? Go ahead, Jada. Amplitude equals
4.
4. Now, here's why I love tan graphs. How does an amplitude of 4 mess with a tan graph? Remember what a base tan graph looks like. So the tangent graph kind of looks like, what does this look like? Do you remember? What algebraic function? If you ignore these pieces. Just this one, what's that shape? Cubic. All right, that looks like a cubic. All right, so, all right, by changing the amplitude, how does that affect the maximum and minimum of tangent? It doesn't. I was like, I love amplitude shifts on tan graphs because it's like, oh, I identified the amplitude as 4. Let me think how I'm going to change my graph. It doesn't. All right, which is the best part. What does affect it, however, is that 2 on the inside. That 2 on the inside, what are we letting represent that? What letter? W, omega. And technically, it's Greek W. Not that it matters when we write it because it still looks like a W. W equals 2. Omega helps us find the period. For tangent, it is pi over omega. Since omega is 2, that means our period is now pi over 2. And again, for tangent, we need 3 points, but that really just, it's not being shifted left, right, up, or down, right? It just changes where our asymptotes are. It's not going to change our start point, just our, or for the tangent graph, the start point is the middle, right? It doesn't change the middle point. It's only going to affect our asymptotes. As far as the graph is concerned, it still looks exactly the same. right? Still looks like a cubic, repeating constantly. We only have to identify where our asymptotes are because the center point is still 0, 0. So if our period got cut in half, right? Remember for a tangent graph, our previous asymptotes were pi over 2 and negative pi over 2. But if I cut it in half, where are my new asymptotes? Pi over 4, exactly. It's this just divided by 2 again. And this is why I love tangent. It's just so easy to see. Pi over 4 plus pi over 4 makes pi over 2. So I know my period is correct. Right? Tangent is the best graph to draw every time. I was like, they're just amplitude, you just ignore, and you start in the middle and then just work to the asymptotes. All right. All right, back to the ones that are the real challenge. All right, so notice that this has a lot going on. A couple of things we need to identify before we even get going. What's the biggest thing? What? Yes, the negative. All right, we have the negative sign, which means the graph is going to be flipped. Which basically means I'm going to ignore that until the very last step. Because it's just such a mess to try and graph the reflection. It's just easier to graph the base function and then flip it. The other big problem on this one is this isn't in a good form. All right. Specifically, this is all multiplied out. And we really need this separated so we can identify the x shift, all right, individually from omega, because currently this value right here, this 4/3, is omega times the x shift. So the best thing to do is factor. And so we're going to turn this into y equals 7 sine, so I'm ignoring the negative entirely, pi over 3. I'm going to factor out pi over 3. Now, the good news is pi over 3x, when I factor pi over 3, that just leaves x. And then 4/3, factoring pi over 3 from 4/3. Boy, that one seems kind of hard. Does anyone know if that doesn't come to you right away, what kind of the simple thing is of factoring? What is factoring a shortcut for? What mathematical operation? Almost opposite of that. Dividing. So actually, what I end up with is 4/3 divided by pi over 3. Because all factoring is because multiplying things together, right? That's timesing, right? Foiling things out, box method. That's all multiplying. Factoring is pulling things apart, which is just it's a fancier way of dividing. This now has everything in the nice form, all right, so I can actually identify my pieces. All right, so my amplitude, just 7. The negative, right, the sign, that purely means the flip, all right? So just, really, amplitude is always an absolute value, so it's always a positive number. All right, omega. What is it?
Pi over 3.
It's that pi over 3. Omega matters because why? What do we need it for? Period. Standard equation, 2 pi over omega, which gives me 2 pi over pi over 3. All right, I'm going to start simplifying stuff down. 2 pi over 1, leave it, change it, flip it. Oh, that's nice. Look at that, 6. Okay, we need to fix this guy too. 4, what was that, 4/3? 4/3 over pi over 3, which equals 4/3 times 3 all over pi, which equals 4 over pi. Okay. Okay. So, actually, this is about to be very bad. And I can see it in the numbers already. When this is shifted by 4 over pi and you have an integer period, all right? We have a cross of pi's and not. Okay, that's good. All right, my x shift, which is phi all over omega. And now I'm putting down, the official Greek letters, but a lot of times people just write x shift, y shift. Whatever is easiest for you, write that. I identify it, in terms of the quote proper, beautiful form that is the initial form of trigonometric general functions, right? But it doesn't matter. What matters is what you actually find, okay? Which is why I try and write it both ways. So whichever one, I like the words, I like the letters better, whichever. All right, and the x shift in this case, what is it? Almost. If this is a positive, right, so actually the x shift is -4 over pi, which is why I wrote this one, right? That's why I was writing this one in this form, just to identify that technically it's the negative value. And you can also write it like that. If you want to write it like that, that's absolutely fine. So I can write an x shift as -4 over pi, or I can write that as left 4 over pi. And it doesn't matter. Whichever one is easier for you, all right? As long as you keep remembering it is the opposite sign of whatever it says. All right, and then just for, I guess for completeness, B equals y shift. What's the y shift here? Brandon, I think you're gonna say something.
There's no y shape.
There is no y shift. Oh, well, that was nice. Finally, we got a break. Okay, so that guy's 0. Okay, so I think I have all my pieces to at least get started with my start point, end point, all that good stuff. Okay, so remember your start point is, right, your x shift. So that is -4 over pi. The end point is your start point plus your period. So our period is 6. And our start point is -4 over pi plus 6. And this is what I was talking about where the numbers aren't good. And there's actually no real good way to do this. -4 over pi plus 6. Now I could make common denominator here, but it doesn't get any better. So I might as well just leave this as 6 minus 4 over pi. And the only thing I am gonna need is to realize what that number is, so how far across the 0 we are. 4 divided by pi. Okay, 4 divided by pi is approximately. Now we're gonna keep it exact, but I need to know these numbers for our starting values. 2, 7. So if that value gets below, actually even, nope, 1.5, we're fine. Okay, halfway. Now, here's another thing. I could keep going and doing those same things again. But if we just leave it as 6 minus 4 over pi, all right, so my period is basically 0, right? Because this is 0 minus 4 over pi to 6 minus 4 over pi. What is halfway between 0 and 6?
3.
Yeah, so it's going to be 3 minus 4 over pi. What's the first quarter? What is a quarter of the way between 0 and 6? 1.5, exactly. And this is why I looked that value up. So I have 1.5 minus 1.27, so this is still a positive number, just so when we graph it, I know where I am on the, against the y-axis. And then lastly, the third quarter. What is 3/4 of the way between 0 and 6?
4.5.
4.5. All right, AKA 9/2 just to keep the fractions pretty. I mean, as pretty as this is gonna get. Okay, so I have all my points. Let's see if we can't graph this bad dog. Okay, so it actually reaches a peak about there. And if I'm drawing a better graph, so I plot the 5 points and then sketch it. Okay, so our points, right here, we have negative 4 over pi. Right here, I have 3/2 minus 4 over pi. This is 3 minus 4 over pi. All right, and then, all right, and again, notice, I was like, when I graphed it, I didn't really bother labeling my y-axis because I come back here and I say, okay, what's my amplitude? Oh, 7. So all my graphs look the same. The only thing that ever changes is a little bit of where is the y-axis and basically what is the scale. And so this is actually 7. And this guy down here is -7. All right, we have all our quarters, we got our shift, period. Only one last little thing, because this, the blue line is actually y7 sine of over 3x plus 4 over pi. But what we're actually going to need is -7 sine. So again, the very last step. All right, I've graphed it, did it as best of job as we could, and the very last step, take all your values and just flip them. And technically, we should always make sure we should always make sure we put the arrows to indicate these graphs are periodic. They go forever, even though we're only graphing one period, right? They do go forever. All right, that's good looking stuff. All right, any questions? Are we all right? Okay. All right, so current in amps, all right, flowing through an AC current at time t is given by the following equation. I want to find the period, amplitude, phase shift, and graph the function. And notice that this one actually has another note. So once we start getting into real context, all right, and since t is time, can time ever be negative?
No.
No. So this is a very, very common initial condition. And so even when things are shifted to the left, all right, when you actually draw the first period, all right, you should cut it off at t equals 0. Now, good news, is this shifted to the left? No. So that at least helps us there. And usually they are not, okay? But it technically could be, and so when you draw it, you can draw that stuff behind, but then basically say that, make sure you indicate this starts at t equals 0. All right, so the biggest thing is to get this into the proper form. So, and because the one thing we need to identify is the phase shift, AKA the X shift. So it's always best just to start by factoring out this piece. So that actually is 190. All right, so our pieces to identify. So amplitude, that's always the easiest one. What's the amplitude? 120. What is our B shift? Actually, this might be the easiest one. Okay, 0. So the Y shift, nothing's happening there. All right, the X shift.
-190th,
Almost.
-190th.
Negative 190. 90th. Yeah, negative 1/90. And what is omega? What is it? Almost
35.
30 pi. And we need that so we can identify the period. And this is really good news. All right, so this isn't that cross we just had. My X shift is a, some fraction, and my period is some fraction, both not involving what? Pies, all right? When one of these has pies, all right, then I know that it doesn't match up. You either both want them to have pies or neither have pies. This we can actually deal with. All right, and actually, since that's 190 though, might also be helpful to just write this as 690s, since we're going to be doing some fraction stuff. Okay, so we have all our pieces. Now we need our 5 points. So the start point, which we know is negative. Oh, my mistake. You were correct initially, Brandon. That is positive 1/90th because it's negative, which actually makes it positive, right? So our start point is actually positive 1/90. The end point is the start plus the period. Which means that's 1/90th plus 1/15, but I've already turned that into, which makes that 7/90ths. And now we need to identify halfway and all that. Which equals start plus the end. Divided by 2. Okay, so 8/90s. Just 2/45. So then it's just fraction work. Similarly, Q1, 1/2 start plus half divided by 2. And similarly, third quarter, which is halfway plus end divided by 2. And that does not reduce. Are we okay? Just fraction math, right? Just breaking it down. We okay? All right. Okay, so we have our start point at 1/90th. And there's no Y shift. And T greater than or equal to 0, so all in the positives. Okay, so we have all our pieces. All right, no Y shift, start, end, and this is sine. And so this is what I was talking about. So, some people like to draw the 5 dots, right? So you go up to your value, knowing what the basic sine graph is, because we know that this value up here, that's 120. Down here, that's negative 120. And then connect all the dots. And this won't even go 1 period, so it's graphs ends there-ish. And we should have all the info we're looking for. All right. Piece by piece. All right. The hardest part, the slowest part, all right, is identifying those 5 points. Okay. The most important part is identifying all the info initially, but this is just kind of a grind, all right? Just do your best, don't mess up usually at this stage, all right? That's the biggest thing, because this one was easy. This was actually just normal fractions, no pies, right? So use your calculator, that's what it's there for, all right? And just grind through that, because getting those 5 points, right? It's all about that X scale. The Y scale is crazy easy. Okay, the Y scale is never difficult. It's always the X scale that takes the time. Okay, all right, we could look at this one, but we're not gonna be able to get through all of it. So, all right, we will pick it up there next class. There is a wonderful activity if you want. Otherwise, all right, we can take a look at the stuff next time.